Hello, my name is Lino. This is a demo video for my thesis project, HiperVR. HiperVR is a VR data analysis tool that helps users visualize trends among data attributes, and it utilizes a 3D scatterplot in the context of HPCC, or High Performance Computing Center at Texas Tech. HiperVR is a web application developed using A-Frame for the VR aspect and 3GS for the 3D aspect. And it uses a data set of servers held statuses from the HPCC Center. Review is an overview of the HiperVR. This is using the desktop version of the system. It can be accessed via web. You can also access it using the Super Medium platform on the Oculus Rift or from the mobile, and you can use the Google Cardboard to see it in VR. You can rotate your head by clicking on the screen and dragging the camera, and for movement you can use the WASD keys in your keyboard. HiperVR consists of a series of different features. Some of them are the physical representation, control panel, host dossier, and the 3D scatterplot matrix. And it also uses a series of logic operations, and then I'll go into some of the challenges when developing this application. So first of all, the physical representation consists of the room and the racks. So the room is aimed to represent the server room at HPCC, and it also supposed to provide a sense of familiarity for the user, and it serves as a reference point. So the user is not he doesn't or she doesn't get dizzy from navigating in an empty world. And the racks, the one you can see over here, they are representation of the racks in the actual room. There are 10 racks, each with 60 hosts, and each host is color coded based on a selected service. So right now we can see there's a gradient color right there. So this is from the default service, which is temperature. So the image right now shows the 10 racks being loaded with the information of the first timestamp. So the default service is temperature. So right now all of these colors are the temperature for each of those CPUs at the first timestamp. Once they are all loaded, the second timestamp information will be loaded afterwards. These colors help the user see right away if one of the CPUs or hosts are having some trouble. So for example, some of those orange CPUs might have some issues, and the green ones, they're probably healthy. So now onto the control panel. So the control panel is made up of three smaller controllers, so time, service, and the diagnostic filtration. And these are mainly to allow the user to interact with the room. It, of course, controls the racks, the scatterplot matrix, and the overall information that is being visualized. So firstly, the time controller is the one above, the one that looks like a clock. So that one controls the current timestamp among the system. So if you were to select timestamp 14, those racks that you saw previously will show the information for temperature in the colors. Then the service, which is the middle one, that one controls the current service among the system and is represented by the color scheme. So the color scheme, we saw them on the racks, and right now it's starting with the default service temperature. So, and we can change it to power usage, fan speed, and a couple others, and they all have different color schemes. And the last one is the scatterplot filtration. So this one controls the filtering of the scatterplot matrix. We're going to talk about more later, but this pretty much controls the filtering of the scatterplot, so we don't have to render all of it. This is a closer look to the smaller controllers. So first we saw the timestamp controller, which controls the time. You can click on each of the timestamps and it will show the information for that timestamp. If you don't click on it, it will continue updating automatically sequentially until it reaches the last timestamp. And then the service controller, this one only changes whenever the users clicks on a different service. The default one is temperature, and you can see here that we change it to the CPU load. And then the last one is the signature filtering controller. And this one is a little bit more complex because it has around 10 matrix, and for each one of them we can set a different value. So we can filter the 3D scatterplot matrix. Another feature included in HiperVR is the host dossier. This feature is imported from the HyperView system. This system was developed by the iData Visualization Lab at TTU. And that system also focused on the health statuses of HPCC servers. And so this dossier pretty much shows a specific view of each host as the one that we saw in the racks. So on the top part, we can see a line graph that shows temperatures of both CPUs along the many timestamps. So for example, this one is the host 9 is the host 17 in rack 9. And we can see the overall change in temperature. And in the bottom part of the dossier, it shows a radar graph, and this one shows all of the hosts' health data. So we can see, for example, the CPU1 and CPU2 temperatures. We can see fan 1 and fan 2 speed, among many others. So this is pretty much specific to one host. Instead of looking at the whole rack's coloring. So the last and probably the most important feature of the HiperVR is the 3D scatterplot matrix. And this matrix provides an overall trends and pattern visualizations. So it visualizes relationships and associations among the attributes. So it can visualize up to 4 attributes per scatterplot, since it has 3 axes, and then one more for the color of each of the data points represented inside of the scatterplot. So in the traditional scatterplot, we will probably have put the 7 services in one axis and the other 7 services in another axis. So this would have given us the combination of 2 attributes per scatterplot. But if we wanted to represent more, the scatterplot matrix would have changed possibly to the one in the right. And we can see that it might be a little bit difficult to navigate through that and probably see attributes in each of the axes, right? Like for example, the y-axis, they probably, if you want to look at one of them, it will probably obstruct your vision. So to overcome that, we took this 3D scatterplot matrix apart in the z-axis, and we came up with a divided 3D scatterplot matrix as the one that you're seeing right now. So each one of these 2D scatterplot matrix are a division of the original 3D scatterplot matrix. And so each one of these is a part of the z-axis of the original one, and we can see that they go small to big because each one of them is supposed to be in front of the other one to follow the same series of 7 services in each axis. So for example, on this one right here, we can see that the x-axis for this is CPU load, the z-axis for this is fan speed 1, and then the y-axis is just up to down according to these ones right here. But the z-axis for all of these is the memory denoted at the corner right here. So for this one is memory load. So we can see that each these points are located in wherever the information for that service is specified. If we look closer to each one of these scatterplots, we can see a range, and this range is just a range for that specific server. So there's a lot of information encoded in each one of these scatterplot, and more especially in the whole scatterplot matrix. Some of the patterns that we can see, for example, in this middle one, we can see that memory load is highly is correlated with the fan speed 1 and 2, and also a little bit with the CPU load. And we can see this because all of the data points, they follow a straight line. So for example, this one, the fan speed, they do not change that much, but the memory load, it changes throughout in a certain manner, right? So if we continue, uh, so now we come back to the diagnostic filtering. So as we saw, some of those scatter plots did not appear in the matrix, and that's because some of the challenges for system is that each scatter plot contains around 400 points, and there's 35 scatter plots. So for this application to be rendered in the browser, it gets very computational heavy. So that's why we also introduce filtering to overcome that, and also to allow the user to find specific trends in each scatterplot. So for example, we can see some of the matrix right here, and these are the matrix that are in the diagnostic control panel. So for example, if the user wanted to see only the scatter plots that have a really high outlying score, he or she will be able to input that on the control panel, and the scatterplot matrix would only show the scatterplots with that outlying score or more. So in the previous view, some of those scatterplots did not show because either they didn't meet the filtering requirement, or some of the data was just corrupted or non-existent, and that's why the scatterplot couldn't have been rendered. So as I said, the diagnostic filtering hides non-variable scatterplots, and it filters based on a series of diagnostic matrix. You can also combine them. You can also say, okay, I want a high outlying score and high clumsiness score. So for instance, in this picture, we can see two scatterplots matrices. The first one is a non-filter matrix. We can see that there's some scatterplots that their data is, some of them is non-existent, but pretty much it's all they all appear there because it's unfiltered. But let's say that we just wanted to see the scatterplots with outlying score greater or equal to 0.2. So if we click that on the control panel, we can actually see those scatterplot matrix disappear, those scatterplots disappear, and the rest one, they will still show. So all these filtering, it happens also during the automatic change in timestamp. So this is, let's say, timestamp 3, and then when it changes to timestamp 4 automatically, it will do the rendering one more time and show the scatterplot for that timestamp. Another thing about the scatterplot filtering is that whenever the timestamp automatic update is occurring, uh, some of the scatterplots that were previously filtered might again meet the requirements, so they will show up um, later on. So for as we saw previously, the scatterplot matrix, it's only usually for overview of the whole system, but we can focus on specific scatterplot. So this is pretty much to get a close-up to each one of them, and we can observe how cell data changing throughout time. And we can see also the access text labels. So many of the complaints about this system, about the 3D scatterplot visualization, is that the accesses are not very intuitive. So we decided to add them in the focus view of each scatterplot. So as we saw in this picture right here, we're clicking on a scatterplot matrix, on a scatterplot, and then it will come forward to the user and it will display the ranges and the access labels. And on this one right here, we can see how each point is moving to the new timestamp information. So some of the logic operations that occur all throughout the running of the system is, for example, at the start, the racks are colorless, all the points start at 0, 0, 0, and all the filtering is set to outline greater or equal to 0.2. So after the start, all of the racks are getting colored, all of the scatterplot points get to their corresponding position, and the filtering, that one's done intentionally again to avoid having to render all of the points at the same time. And then there's the auto update every time. Whenever timestamp changes, it has to update all of the host colors and all the points positions every time. That is quite intensive, especially for the 3D scatterplot matrix. But that's definitely going on in the browser. Everything's in the browser. And lastly, the scagnostic. So all of those matrix, they come from a scagnostic library. And this is run after each timestamp information is loaded. And it does 35 simultaneous calls. So this system utilizes a little bit of parallelism with the promises. So all these 35 scagnostic calls, each one of them is very heavy, especially because of the data that is being computed. So doing 35 is quite heavy. So all of those are being computed uh, in the same time, in parallel. So some of the challenges, there's a high number of objects, materials are being updated constantly, positions are being updated, and there's continuous movement as well. So this is one of the neat features of the system. Whenever you click, for example, on one of the scatterplots, you can see it moving um, in progress, right? So 3GS doesn't have that capability. 3GS, you can tell an object to move, or pretty much teletransport from one point to the other. So to give the user a better experience, we interpolated movements as the one that you're seeing right now with the scatterplot. So we're transporting the object 20 times, so the user can see that it's being moved slowly. And again, this is just to give the user a better experience, so he or she feels more comfortable using our system.